Problem 2-4 is a really good example of how mixtures work. So actually the distribution of x in problem 2-4 is a finite mixture. And how so? Well, let's take a look at what we have in problem 2-4. In problem 2-4, we have a house in the Caribbean, or we own some property in the Caribbean. Let's just think of it as a house. Then the exercise tells us that a storm is coming, and it will probably destroy the house. And in the exercise, they say, well, the storm can have 3 different strengths. With probability P1, the strength of the storm is equal to 1. With probability P2, the strength of the storm is equal to 2. And with probability P3, the strength of the storm is equal to 3. And depending on the different strengths of the storm, the distribution of the loss conditioned on the strength will differ. So if the strength of the storm is 1, then the loss will be exponentially distributed with parameter lambda 1. If the strength is 2, the loss will be exponentially distributed with parameter lambda 2. And if the loss is 3, then if the strength of the storm is 3, then the loss will be exponentially distributed with parameter lambda 3. Now, how does this fit into the whole mixture distribution setup? Well, let's take a look at the book. It says a finite mixture consists of a random variable n with certain point probabilities and some conditional distributions that are the distributions of x given that n takes certain values. So that fits very well with our setup because we have a random variable, strength of storm, that has certain point probabilities, and depending on what that strength of storm is, then x will have different conditional distributions. So in our case, we have that the probability that n is equal to n is given by Pn for n taking values 1, 2, or 3, where n denotes, well, what does it denote for us? It denotes the strength of the storm, right? Strength of storm. And that value can be either 1 or 2 or 3, as given in the exercise. And what we then have is that the conditional distributions fn of x, well, they are the distribution functions that belong to the different exponential distributions, right? So just a really, really quick reminder here, that is the distribution function of an exponentially distributed random variable with parameter lambda. So has distribution function. It has distribution function 1 minus e to the minus lambda y, right? For y greater than 0. So this is something you probably know from SS. So this distribution function here, given that the strength of the storm is equal to n, where n is either 1 or 2 or 3, then the distribution function of x will be 1 minus e to the minus lambda nx, because x is exponentially distributed in all cases, but depending on what n is, it will have a different parameter lambda n. So this is our fn of x. Then they tell us, then by 412, we have that the distribution function of x. So up here, this is the conditional distribution function of x. It's conditioned on if n is equal to 1 or n is equal to 2 or n is equal to 3. But the total non-conditional distribution of x is given by the sum from 1 to 3 of the different probabilities of each of the storm strengths, and we use those to weight each of the distribution functions as such, each of the conditional distribution functions. So they actually say by 412. If we take a look at 412 in the book, what it basically tells us is this. So 412 in the book, the formula 412 right now is on page 41, tells us that if we want to find the distribution function of x, and we happen to know the conditional distributions of x given certain things, where those certain things are all together, added together events that are disjoint and give you a complete probability of 1, then the distribution function of x is given by the sum of the conditional distributions of x. So the sum of the conditional distributions of x given n for the probability of n equal to n weighted on each of the conditional distributions, where we let n go from 0 to infinity. So this is the general version we have from 412. And when we take a look at our specific case here, then we can see that our conditional distributions are actually our fn's, and our point probabilities that we use to make a weighted average of these conditional distributions is given by the P1 and P2 and P3. So this is the case where we get the distribution function. The thing is, how about the density function then? Because what we're interested in 2.4, the problem 2.4, is the density function of x. Well, luckily that's not too hard, because the density function is just the derivative of the distribution function, which means that the density function is just this thing above, but where we, instead of using the conditional distribution functions, we use the conditional densities. And we know the conditional densities because each of them are just exponential densities with respectively lambda 1, lambda 2, and lambda 3 as their parameters. So this is the general formula that we use to solve problem 2.4. Now, note what this fj actually stands for. This is what I want to end this part with. This fj, this actually stands for the conditional probability of x given n, so given storm strength. So the not conditional probability, the conditional density of x given n, evaluated in x given a certain value of n, which in this case is j. So if it was f1, then it would be the conditional probability of x given that n is equal to 1. If I had written f2, then it is the conditional probability of x given that n is equal to 2. So here you have the general formula that you use to find the density in the case of a finite mixture. The reason why I just wanted to bring in this part of the book and talk with you guys about it is because a lot of people get confused over what mixture distributions are, because the notation is kind of confusing. It's a bit hard to understand, but essentially this is just what mixture distributions are all about. It's the case where something happens, and depending on what happens in the beginning, then the loss or something else will have distributions that vary. So in our case, it is a storm hits, and depending on the strength of the storm, the damage done to the house will follow different distributions. Other cases where we use mixtures can be, for example, with car insurance, where we think of the fact that, well, depending on who is driving the car, then the distribution that tells us of how much damage will be done to the car if there is damage will vary. So when we look at a whole population as a whole, if we know that there is 40% women and 60% men in this population, then we will probably take a total distribution of loss by saying 40% multiplied by the loss density for women drivers, for female drivers, and then plus 60% multiplied by the loss density for male drivers, for example. So these are just different examples of when we use mixtures, and here you have one concrete example.